Howdy. This is Mr. Potter. Welcome to section 3.6. In this lesson, we're going to be talking about composition of functions and a rule called the chain rule, which helps us deal with derivatives of compositions of functions. So I first want to start about talking about decomposition of functions, because in our pre-calculus class it was really important for us to understand how to write two functions as this composition of function. You may remember the f of g notation or this f of g of x notation. What I want to start off with today is I want to work backwards through some of these functions. So let's say that I tell you that y is equal to sine of 3x plus 1. And the thing is, I want to write this as f of g of x. And so the question is, looking at this function, can I identify what my outer function is and what my inner function is? Well, if I was to substitute it into a calculator, the last thing that I would do is to find the sign of my argument. So my outer function f is going to be the sign of something. So I'm going to call this f of u. And my u in this case is my g of x, which is what I'm taking the sign of. In this case, it's 3x plus 1. So what I really have is f of g of x, the sign of 3x plus 1. And given a complicated function like this, I need to be able to decompose it into its two constituent functions, the f and the g. So if I was to do another example, say y equals the sine of x over 1 plus the cosine of x squared, then there's something that's happening that's definitely the last step. My f of u in this case would be u squared, where u is my g of x, this rational function sine of x over 1 plus the cosine of x. And one more example, let's say I told you that y is equal to x squared plus 1 quantity cubed. In this case, the very last thing that's happening is I'm cubing an expression. And the expression that I'm cubing, which is my g of x, is x squared plus 1. So given a complicated function, a composition of two functions, I need to be able to recognize the parts that make it up. I need to be able to decompose my functions into an outer function and an inner function, and maybe even multiple layers. So I want to go through one example. The last example we did, where we had y equals the quantity x squared plus 1 cubed. And I want to take a look at the derivative from a couple of standpoints. The first standpoint that I want to look at is if I was to expand this by multiplying this binomial times itself 3 times. And if I did that, I would end up with x to the 6th plus 3x to the 4th plus 3x squared plus 1. And if this is my function y, then my derivative would just be the power rule here, which would be 6x to the 5th plus 12x to the 3rd plus 6x. And of course, the derivative of a constant is 0. If, however, I look at my original function and I remember, hey, we decomposed this. We said that f of x is really, or f of u is really u cubed, where u is my g of x, which is x squared plus 1. If I take a look at these derivatives, f prime of u in this case would be 3u squared, and g prime of x would be 2x. But remember that u is still this g of x, this x squared plus 1. So this is really 3 times x squared plus 1. And if I was to distribute this out, I'm going to have 3 times x to the 4th plus 2x squared plus 1. Or 3x to the 4th plus 6 x squared plus 3. And I notice that this has some relationship with what I originally found as my derivative. But it's not just as pure as doing the power rule, the derivative of u cubed being 3 times that function squared. I'm off by a factor. And this factor is 2x, because if I was to take 2x times 3x to the 4th plus 6x squared plus 3, I find out that I get 6x to the 5th plus 12x cubed plus 6x, which is exactly what I've got here. So in other words, it certainly appears that if I have a composition of functions, f of g of x, and I want to take the derivative of this, I should be taking the derivative of f with respect to my inner function g of x, my inner function u. and then multiplying it by dg dx, because I was off by a factor of 2x. It wasn't until I actually distributed the 2x that I got the true derivative. And so this rule in calculus is called the chain rule. The idea is that whenever I have a composition of functions, I have to take the derivative of my outer function and then take the derivative of my inner function. And these functions are linked together in this chain of taking derivatives. So what I want to do now is I want to prove this chain rule. So I want to prove that the derivative of f of g of x is the derivative of f prime evaluated at g of x times g prime of x. In other words, the change in f with respect to u times the change in g with respect to x. And so what I'm going to do is I'm going to fall back to the definition of the derivative. This is supposed to be the derivative of f of g of x and that's going to be the limit as h approaches 0 of f of g of x plus h minus f of g of x all divided by h. And I'm looking at this, and this is kind of where we were when we were dealing with the product rule or the quotient rule. In and of itself, I don't have a lot to work with. I need to introduce some more terms. A little bit different from how we did it before. We used to add a clever form of 0 by adding and subtracting a term. What I'm going to do here is I'm actually going to multiply by a clever form of 1. In other words, I'm going to take this f of g of x plus h minus f of g of x divided by h. And I'm going to multiply by this rational function, g of x plus h minus g of x over g of x plus h minus g of x. Now, I'll explain where this came from in just a moment. But suffice to say, multiplying this fraction times 1 isn't going to change the value of my derivative. And whenever we multiply fractions, we multiply the numerators and we multiply the denominators to get our new numerators and denominators. But the order in which we multiply isn't essential. So I could rewrite this as f of g of x plus h minus f of g of x over g of x plus h minus g of x times g of x plus h minus g of x over h. And one of the products of limits is that the limit of a product equals the product of the limits. So I can break this up into two limits. And now I think you see where this comes from, or where we're headed with this. This is the g prime that we have here. So this is the derivative of g. What's not so clear is what I've got over here. And so what I need to do here is I need to do a little bit of a substitution. So I'm going to let u be g of x, which is kind of the substitution that we had talked about on the previous page. U is what I'm taking the function f of. It's f of an expression, and that expression is g of x. And I'm calling that really f of u. But if I do this, then I really want to say that u plus k is going to be how far g of x plus h is from this value. And so what this allows me to do is this allows me to look at the limit as k approaches 0 of f of u plus k minus f of u over u plus k minus u. And so what I've really got here is my u's subtracting out, and this is another definition of the derivative. But this is not just any derivative, this is the derivative of f prime of u. And that's being multiplied by g prime of x. So what I've got here is that the derivative of f of g of x is really f prime of u times g prime of x, or df du times dg dx. And so we have this chain rule now that allows us to take the derivative when I have a composition of functions. So I want to go through some of the examples that we talked about earlier. So one of the examples we had was, what if I have f of x being equal to the sine of 3x plus 1. And we talked about how to break this up into its component functions. In this case, f of u is really the sine of u, where u is the expression 3x plus 1. So if I want to find the derivative of my function, this is going to be equal to f prime of u times g prime of x. And the derivative of sine is the cosine of u. And the derivative of 3x plus 1 is just 3. So I've got the cosine of 3x plus 1 being multiplied by 3, or 3 times the cosine of 3x plus 1. So I'm able to take the derivative of a function that was rather difficult to take the derivative of before. But being able to break it down into its constituent functions, being able to decompose this function, and then take the derivatives of each part, allows me to find the derivative of this composed function rather easily. So we'll do another example. We'll do the y equals the quantity squared sine x over 1 plus the cosine of x. And so what I've got here is I've got two functions. F of u is u squared, where u, my g of x, is this fraction, sine x over 1 plus the cosine of x. And so I know that the derivative of f of u is 2u, and the derivative of g, well, this is a little bit more involved. I've got to use that quotient rule. Quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And when I take this derivative, I'm going to have 1 plus the cosine of x times the cosine of x minus the sine x times negative sine x over 1 plus the cosine x squared. And I see some things happening. First, if I distribute this, I'm going to have cosine of x plus the cosine of squared x minus, this is really negative sine times negative sine, so this is really plus sine squared x. And I think you see what's going to happen there. Over 1 plus the cosine of x squared. And so what I've got here is I've got 1 plus the cosine of x over 1 plus the cosine of x squared. And I've got some algebra that happens here. So I end up with 1 over 1 plus the cosine of x. This is g prime of x. Now it was perfectly it was perfectly fine for me to stop at this point. But if I continue doing the algebra, I've got a much simpler function that's going to be multiplied by 2u. U in this case was my original g, sine of x over 1 plus cosine of x, which I'm multiplying by g prime. And you see that I've got 2 sine x in the numerator and 1 plus the cosine of x squared in the denominator. And so this allows me to deal with a very complicated function through a series of the steps that we've learned. We've talked about the power rule. We've talked about the quotient rule. And we've talked about using algebra to simplify these functions. So I end up with a very simple derivative just by using a little bit of algebra. I want to go through a couple more examples because this chain rule is probably one of the most tedious parts of calculus. It's one of the things that most students have difficulty grasping. And so practice is the only way that you're going to get better at this. So I want to do 2 more examples. The first example I've got is y equals the cosine of x squared. Please note this is not the same thing as cosine squared x, because my f of u and my g of x are distinctly different functions. Order of operation says that I'm supposed to square first and then take the cosine of this. So f is my cosine function, where g is x squared. So if I take the derivative of cosine of u would be the negative sine of u, and the derivative of x squared would be 2x. And so I've got the negative sine of u, my original u, x squared, times 2x is really the derivative of my original function y. And I can rewrite this as negative 2x times the sine of x squared. So again, it's this composition of functions, being able to take an original function and breaking it down into its two components, taking the derivative of each one of these components separately, and then combining them in the appropriate order. This idea of the derivative of f with respect to u times the derivative of u with respect to x, where u is g. So I want to do one more example of this. I want to take a look at a function that it is algebraically simple. I've got x plus 2 raised to the 9th, but I certainly don't want to try and expand that, multiplying 9 factors out. It's going to be much easier for me to take a look at this as f of u being u to the 9th, where u is my g of x, or x plus 2. So the derivative of u to the 9th would be 9u to the 8th power, and the derivative of g is just 1. And so I end up with my derivative of my original function being 9 times u to the 8th, where u is x plus 2. Now, if I had expanded this and taken the derivative of all 10 terms of this polynomial, there's no way that I would have figured out that that would have been a very nice factored form in its derivative form. And I wouldn't know that without the chain rule. And that's one of the powerful aspects of the chain rules, that it allows us to deal with very convoluted, complicated functions in a very straightforward manner. So the main idea of this chain rule is that if I want to take the derivative of a composition of functions, f of g of x, I'm going to take the derivative of the outer function, evaluate it at my inner function, and I'm going to multiply that times the derivative of that inner function. This is the chain rule, and in our next lesson we're going to talk about how does this work when we have a composition that's 3 levels deep, or that's 4 levels deep, because this rule still works. What happens is this g prime of x is something that we would have to just further break down. But we'll talk about that tomorrow. This is Mr. Potter. Thank you for watching. Have a great day.